All right, today we're going to do chapter 19, which is electrochemistry. And we start off doing oxidation reduction because your electrochemistry, you're going to have two cells. You're going to have your anode and your cathode. You're going to have your oxidation half reaction, and you're going to have your reduction half reaction. All right, so when we talk about cells, we're going to talk about a voltaic cell. We're also going to call this a galvanic cell. All right, so it has two names. Voltaic cell, the classic name is the galvanic cell. Anytime you see that term, that tells us that this is a spontaneous reaction. All right, so we know that the delta G here is going to give you a negative sign. It is a spontaneous oxidation reduction reaction. So that is, you get all of that from just the term a voltaic cell. All right, so if it says voltaic cell, then you have a spontaneous reaction. All right, so we did this half reaction method back in chapter 4. All right, and we did some acid and base solutions. This one is going to do pretty much exclusively in acid and base solutions. Remember, if it says in acid, we're going to balance the charge with H+. If it's in base, we balance the charge with hydroxide, OH-. I also note that the book does not do it that way. If you do it the way the book does it, I don't care, but I do not like that way near as much as the way I do it, so I will only do it the way that I do it. All right, so we need to first identify what's being oxidized and what's being reduced. All right, because when we do oxidation reduction, step 1 is get all of the oxidation numbers. All right, so we're going to have to give the oxidation numbers, and whatever numbers are changing, if it's increasing, it's oxidation. If it's decreasing, it's reduction. And so then we know our oxidation and reduction half reactions. All right, so second, you identify the species. Yeah, right. The one changing oxidation, that's what we're looking for here. And then in the problem, it will either state acid or it will state base. All right, so let's go and do this one, or I'll just do a different one altogether. Let's go do a different oxidation reduction problem. You can work through the one that's in the book. All right, I'm going to pick one that is a little more challenging, which goes through all the steps, well, almost all the steps. Cr2O7 minus 2 plus C2O4 minus 2 yields Cr plus 3 plus CO2. And this is in acid. All right, so, and this would be balance this oxidation reduction reaction using the half reaction method. All right, so we have to get our oxidation numbers. We need the oxidation number for Cr, for O, for Cr, or for C, for O, for Cr here, for C here, for O here. None of these are peroxides. All of the oxygens are minus 2. The only time oxygen in a compound is not minus 2 is if it is a peroxide. None of these are peroxide. All right, so the only peroxides that you would have to know would be hydrogen peroxide or any of your group 1s or group 2s. Remember group 1? All right, so your first column, group 1, always plus 1, no exceptions. Group 2, in compounds, always plus 2. All right, so if you see hydrogen with sodium and it's Na2O2, all right, sodium is always plus 1, never any other oxidation. Oxygen is plus 2 unless it's a peroxide. It's definitely not plus, or it's minus 2 unless it's peroxide. It's definitely not minus 2 here because that would make the sodium plus 2. All group 1s in compounds, always plus 1, always. All right, so Group 1 metals, because of course in group 1 is hydrogen, which you could also have as a -1. So if you had NaH, again, sodium is always a +1. It is in a group 1 metal. Group 2 metals in the column, the alkali metals alkali metals are always +1. That is group 1. The alkaline earth metals, group 2, periodic table, always +2. So if you had, let's say, MgO2, all right, so we know, we did the experiment, we made magnesium oxide, it's MgO, because Mg is +2 and oxygen is -2. All right, what we know for sure is Mg is always +2 because it is an alkaline earth metal. All right, and so here, this is magnesium peroxide because the oxygen can be -2, or in the peroxide, it could be -1. All right, so anyway, none of these are metals that could be a possible peroxide. If it is a peroxide and it's not an obvious one, I would have to state that this oxygen is a peroxide. All right, so in compounds, oxygen is always -2. All right, so there's 7 of them here, so that's -14. So these 2 CRs have to be +12. 12 minus 14 is a total of -2. All right, I didn't want 2 CRs, I wanted 1. So each one of these CRs is +6. Here we have oxygen -2, there's 4 of them, so that's -8. 2 carbons is going to be +6, because 6 minus 8 is the total charge, overall charge of -2. I didn't want 2 carbons, I wanted 1. So each carbon is a +3. A monatomic ion has the oxidation of the charge. So this is a +3 oxidation number. Again here, -2 for your oxygen. You got 2 of them. That's -4. The overall is neutral. And so you have a carbon that is +4. All right, so that is always step 1, is give your oxidation numbers. And so we see that Cr is going from a +6 and it is reduced to a +3. This is going to be your reduction. All right, and so a reduction is a gain of electrons. All right, and so this is gaining 3 electrons per Cr, because each Cr on the left is going to be +6, each Cr on the right is going to be +3. So you had to gain 3 electrons per Cr. For your carbon, you see the carbon is going from a +3 up to a higher oxidation, a +4. So this is your oxidation half reaction. All right, and so we are going to lose 1 electron per carbon. We're going to lose 1 electron per carbon. All right, and so we're going to break this into our 2 half reactions. So we have our Cr2O7 -2, and it is going to our Cr +3. All right, so the first thing we have to see is that we're going to balance everything that is not hydrogen or oxygen, which means we're going to balance the atom changing oxidation number. So you see that we have 2 CRs that are +6. On the right, we only have 1 CR that's +3. If you have 2 CRs on the left, you must have 2 CRs on the right. And so that's why I said that you're going to gain 3 electrons per CR. We have 2 CRs. So we have to multiply that by the 2 CRs. So we are going to gain 6 electrons in the half reaction. We are going to gain 6 electrons in this half reaction. All right, and so this is your reduction half reaction. All right, for the oxidation half reaction, we have C2O4 -2 going to CO2. All right, on the left, we have 2 carbons at +3. On the right, we have 1 carbon at +4. If you have 2 carbons on the left, you must have 2 carbons on the right. And so we are going to lose 1 electron per carbon, but we have 2 carbons. And so we are going to lose 2 electrons. We are going to lose 2 electrons. All right, here is your oxidation half reaction. All right, so the electrons were used to balance the oxidation numbers. All right, so you have to use electrons to balance oxidation numbers. All right, and so you have your oxidation, releasing electrons. You've got your reduction, taking and gaining those electrons. It is a transfer of electrons. It is oxidation reduction. All right, so the first thing that we do is we get our oxidation numbers. The second thing, we break it into 2 half reactions. The third thing we're going to do is we're going to use electrons to balance our oxidation numbers. So once we have balanced our oxidation numbers, we are now going to balance the overall charge. All right, so now we're going to balance the overall charge. So, yes, 1, you get your oxidation numbers. Should have went down further on this one. 2, we get our oxidation numbers. 2, we're going to balance oxidation numbers. Fine. Break into 2 half reactions. Into oxidation and reduction half reactions. All right, and so we assigned our oxidation numbers, we broke it up, and then we balance our oxidation numbers with electrons. So now we're going to balance oxidation numbers with electrons. All right, so now we're on step 4, which is balance the charge. So step 4 is going to be balance the charge. We did not balance the charge with electrons. We balanced our oxidation numbers. Now we're going to balance the overall charge. If it says acid, which this one says, it's H+. If it's base, then you would use OH-. All right, so we look at our problem, and it gives the reaction, and after the reaction, it says acid. And so you're going to see either it's going to say it's an acid or it's going to say it's in base. All right, so now we see that we have to get our charge. 6 minuses, so that's, of course, minus 6. 2 minuses, that's minus 2. So on the left side, we have a minus 8. On the right side, we have 2 plus 3s. We have plus 6. Obviously, minus 8 does not equal plus 6. We are in acid. A very common error is to say you need 2 H pluses. Minus 6 does not equal plus 6. All right, so you have to add 8 H pluses to get to 0. You have to add 6 more to get to plus 6. All right, so you have to add 14 H plus. And now when you add plus 14 to this side, now your minus 8 is plus 6, which is equal to plus 6. All right, down here, we have a minus 2, we have a 0, we have a minus 2. We don't have to do anything. We have a minus 2 on the left, we have a minus 2 on the right. We have a balanced overall charge of minus 2 equals minus 2. All right, now step 5 is going to be to balance the hydrogens and oxygens using water. So we're going to do number 5, balance hydrogen and oxygen using water. All right, so we did not balance the hydrogens. We only balanced the atom that was changing oxidation. Okay, we didn't write that in there. So when you break it into an oxidation and reduction, make sure you are balance the atom that's changing oxidation state. You have to balance the atom changing oxidation state. So if they have a different oxidation number, they have to be balanced. Hydrogens and oxygens will be balanced in step 5. All right, so now we have to balance hydrogens and oxygens. On the left, we have 14 H's and 7 O's. And on the right, we have nothing with H's and O's. So 7 H2O give us 14 H's and 7 O's. On the left, we don't have any H's. On the right, we don't have any H's. On the left, we have 4 O's. On the right, we have 4 O's. We are balanced. There is nothing for the second half reaction. It is already balanced with hydrogens and oxygens. No hydrogens and 4 oxygens on both sides. So after we balance our hydrogens and oxygens, now on number 6, you have to get electrons gained equal to electrons lost. All right, and that is the key to oxidation reduction. Electrons gained equal electrons lost. Right now, we have gained 6 electrons, but we have only lost 2 electrons. All right, and so we have to multiply this by 3. And now we will have 6 electrons gained and 6 electrons lost. So you multiply it through by 3. So now we have 3 C2O4 minus 2s. We now have 6 CO2s. We now have 6 electrons, and we will subtract 6 electrons from both sides. All right, and after we have done that, now we can add up the 2 reactions. All right, so now we're going to add up the 2 reactions. So on the left, we still have 14H plus. We have our Cr2O7 minus 2. We have our 3 C2O4 minus 2s. And that's what we have on the left. On the right, we have 2 Cr plus 3s. We have 6 CO2s. And we have 7 waters. All right, so if we check the charge on the left, we have a Cr2O7 minus 2. We have one of them. We have 14 H pluses. We have 3 C2O4 minus 2. So this is a plus 14. This is a minus 2. This is a minus 6. All right, and so you end up, you got 14 minus 2 is 12. Minus 6 is a plus 6 on the left. On the right, you've got plus 6. You got CO2 neutral. You got H2O neutral. You have plus 6. All right, and so there is your overall oxidation reduction reaction. All right, so that is one in acid. Let's do one in base. My favorite base oxidation reduction is this one. Cl2 goes to Cl minus plus ClO3 minus, and this is in base. The steps are exactly the same. This one is a little strange because we do our oxidation numbers. Cl, it is an element in its natural state, which has an oxidation number of 0. Cl minus, that is a monatomic ion. The oxidation is the same as its charge, -1. We have ClO3 minus. So each O is -2, so that is a -6. So the Cl has to be +5. 5 minus 6 gives an overall of -1. So, oh, we didn't do that. I skipped a step. All right, so when we are back here, we are always going to be asked to label the oxidizing agent and reducing agent, the reduction half reaction, the reactant, the entire reactant, not Cr. Cr is not a reactant. Cr2O7 minus 2 is a reactant. The entire reactant is your oxidizing agent. All right, and of course, the reactant of your oxidation half reaction is your reducing agent, not carbon. There's not carbon in either one of these. All right, there is carbon as part of this molecule, but there is not just carbon. All right, and so this entire reactant is your reducing agent. All right. All right, and so why is it called an oxidizing agent? Well, because if you wanted to oxidize your C2O4 minus 2, we want this to do the oxidation half reaction. You're going to go to the stockroom and look for something to oxidize it, and that is called an oxidizing agent. And so you would add the Cr2O7 minus 2 to your C2O4 minus 2 to oxidize it. And that's why the Cr2O7 minus 2 is called an oxidizing agent. All right, I got to that point because here we only have one reactant. We only have Cl2. And so when you only have one reactant, it's going to be pretty simple. You're going to have, you can write it twice if you want to, so you have two different molecules. And you would say, here is the oxidizing agent. And here's the reducing agent. When there's only one reactant in an oxidation reduction reaction, then it is both the oxidizing agent and the reducing agent. All right, because when we go to break it into two half reactions, we're going to have Cl2 going to Cl minus. We're also going to have Cl2 going to ClO3 minus. All right, and so we can write it twice. All right, so we see that in one of these, we have the 0 going to -1. That is going down. That is a reduction in number. This is your reduction half reaction. All right, and so this is going from a 0 to a -1. So we are going to gain 1 electron per Cl. From this one to this one, we have a 0 going to a +5. So we are oxidizing, increasing our oxidation number. All right, and this has to lose 5 electrons per Cl. And so now we can break it into our half reactions. All right, so if we have our Cl2 going to Cl minus, what you should immediately do is know that if I have 2 Cl's at 0, then I have to have 2 Cl's at -1. You must immediately put the coefficient of 2. And so for your half reaction, you gain 1 electron per Cl, but you have times 2 Cl. And so you're going to gain 2 electrons. So we are going to gain 2 electrons. And that is balancing our oxidation numbers. All right, and so that has been reduced. This is our reduction half reaction, I guess. So this should have been labeled oxidizing agent, but Cl2 is Cl2. It doesn't matter. Oxidizing agent. And this is the reducing agent. What did I just change? I changed Cl2 from the oxidizing agent to the reducing agent, and I changed Cl2 from the oxidizing agent. Okay, you did the same thing. It's both. It doesn't matter. But since I wrote the arrow from the 0 to -1, which is the reduction half reaction, well, then that's your oxidizing agent. All right, so here is your oxidizing agent. The other half reaction is Cl2 going to ClO3 minus. And again, you see 2 Cl's at 0, you see 1 Cl at +5. You immediately have to put the coefficient of 2 and see that we are losing 5 electrons per Cl. And in this half reaction, we also have 2 Cl's, so we are losing 10 electrons total. And so to balance those oxidation numbers, you need 10 electrons. So now we have balanced our oxidation numbers using electrons. Here is your oxidation half reaction. And this is your reducing agent. All right, so after we balance our oxidation numbers with electrons, we balance our charge. Charge on the left here is -2, 0, total -2. And on the right, -2. We are done with that one. It is balanced. On the left here, we have a charge of 0. On the right, we have 2 minus 1s. We have 10 minus 1s. We have a total of minus 12. Now we are in base, so when you're in base, you use OH minus. And so we are going to need 12 OH minuses. And now we have minus 12 on this side, and we have minus 12 on the other side, and we balanced our charge. All right, so after we balance our oxidation numbers with electrons and balance our charge with OH minus because we are in base, now we balance hydrogens and oxygens with water. First one, there's no hydrogens or oxygens on either side. They are balanced. All right, the one on bottom, we have 12 H's and 12 O's on the left, and on the right, we have 6 O's. All right, so we need 6 more oxygens to equal 12. So we need 6 H2O. That gives us 6 O's here, plus the 6 O's here, give us the 12 O's. Our 12 hydrogens from 12 OH minuses, 6 H2O's is 12 hydrogens. And so now we have a balanced oxidation half reaction. So now that we have balanced both the oxidation and reduction, now we're going to add up our two half reactions, making sure that our electrons gained equal our electrons lost. Right now we have gained 2 and lost 10. So we have to multiply this through by 5 in order to gain 10 electrons and lose 10 electrons. All right, and so now we have 10 electrons, we have 5 Cl2s, and we have 10 Cl minuses as I multiply it through by 5. And so we subtract 10 electrons from both sides. The 10 electrons from both sides are gone. And so we can then add up our two half reactions. We have 12 OH minus plus 6. All right, so we have 5 Cl2s here, but we have 1 Cl2 here. So 5 Cl2s plus 1 Cl2 is 6 Cl2s total on the left side. And that yields 10 Cl minuses and 2 ClO3 minuses and 6 H2Os. All right. Always want to check your charge. Make sure you didn't forget to bring something down. All right. So you got minus 12. You got 0. You got minus 10. You got minus 2. You got 0. So we have minus 12 is equal to minus 12. So we have a balanced oxidation reduction reaction. If you leave it like this, you will lose a point. You did all the work. Everything is correct. The only problem is when you have a balanced chemical reaction and all of your coefficients are even, you will not be getting full credit. That is not in lowest terms. And so they all have a common factor of 2. And so to get full credit, you have to divide the whole thing through by 2 or multiply the whole thing through by 1/2, however you want to look at it. So your final answer is 6 OH minus plus 3 Cl2s yield 5 Cl minus plus ClO3 minus plus 3 H2O. And so now we have a minus 6 and a minus 6. It's still a balanced chemical reaction, but now it's in lowest terms. The book does not do it this way. You can follow the rules of the book, and that's fine. I will not use those rules because they don't balance the oxidation numbers using electrons. They do it some other way that is a way to get the answer, but not the way it should be taught, in my opinion. So it will get you the right answer. It's not easier. It's not harder. It's pretty much the same, but it's not a feel of exactly what's happening. All right, so now we're going to do some galvanic cells. All right, so they go through it. They do it kind of weird. In my opinion, they do it weird because if they're in base, where they do it in base, So if you're following along the way they're doing it, when they do one in base here, pretty much the acid ones are done similar. They just balance things at different times. And then when they add it up, they don't cancel out their electrons. They bring them down and then they cancel it. See here, they bring down the 8 electrons and they bring down the 8 electrons. I do that here and I do that here. I don't bring them down and do it, but it's just minor. But when they do theirs in base, they do the same method. They do it like it's in acid, and then they add OH minus. Again, I don't like that procedure at all. It will give you the answer. I say it's not easier at all, but if you think it's easier, then you can do it that way. But when they're done, I think they'll have a final answer here. Yeah, so when you're done balancing your oxidation reduction in acid, so they do it in acid, and so here's their answer in acid, but the question said base. So now, however many H pluses you have to add that many OH minuses. And then that's, of course, if you're adding it to this side, you got to add it to the other side. So now you're going to have 2 waters on this side, and you have 1 water on that side. Then you got to subtract the water from both sides. It seems a little silly to do it that way, but anyway, that's the way they do it. All right, so to our electrochemical cells. All right, when we have an electrochemical cell, we're going to have electrodes, which are going to be solids that dip into an electrolyte, which is going to be a liquid, in a chemical reaction that either uses or generates an electric current. All right, so if it generates an electric current, it's spontaneous, delta G is negative. If it uses an electric current, then it's non-spontaneous, and your delta G is positive. All right, but there's going to be 2 types, one that happens spontaneously and the other one that is non-spontaneous. And of course, if you reverse a reaction, you go from spontaneous to non-spontaneous. All right, so again, voltaic is what we talked about before. If it's a voltaic cell, it is spontaneous, delta G is negative. The older name, which you will see quite often, is the galvanic cell. These are spontaneous. Delta G is negative. So when it says for this voltaic cell or this galvanic cell, you know it's a spontaneous reaction. If it says you have an electrolytic cell, so an electrolytic cell is one that is non-spontaneous. And so here your delta G is going to be positive. So in order to get an electrolytic cell to work, you're going to have to supply energy to get the reaction to go. All right, so we're going to show a picture of a voltaic cell or any cell. All right, and so you're going to have what are half cells. You're going to have 2 half reactions. You're going to have the left side and the right side. The left side, alphabetically, it's going to be the anode. And then on the right, it's going to be the cathode. All right, and so always when you're drawing it, anode is on the left, cathode is on the right. Oxidation occurs at the anode. So this is your oxidation half reaction. Your cathode, red cat, that is where reduction half reaction is. All right, and so we're going to have electrons flowing outside. They're going to be outside of the cell, usually through a voltmeter, or it could light up a light. It could give a time on a digital clock. Lots of different things that you can use a voltaic cell for. You're also going to have an internal cell, and that's going to be a salt bridge. So it's either KNO3 is a common one, KCl is another. It's a salt that is going to allow the flow of ions in order to not build up a giant charge on either side of your cell. All right, so here is a galvanic cell using zinc as the electrode. So your electrode has to be a solid. All right, and so you're going to clamp your alligator clip to that electrode. So you have your zinc electrode. Your Going to have another electrode on the cathode side. Again, it has to be a metal, something that you can clip your alligator clip to. So in this example, we have zinc, we have copper, very common cell. All right, and so on the left is always the anode. So this is your anode, and on the right is always your cathode. Easy to remember, it's in alphabetical order. Red cat, so you know that cathode is your reduction, and your anode is your oxidation. So if we look at this reaction and we see that our zinc is at the anode side, it is doing the oxidation. So we have zinc solid metal going to zinc plus 2. All right, so what's happening, and they're showing in this picture here, is you have solid zinc on your electrode. And that solid zinc is going into ions, so into solution. And so you see that you have an atom of zinc going into a zinc plus 2 in solution. And so you can't really tell in this picture, but this zinc is getting smaller. As this reaction goes, that zinc, the metal is now going into solution. And so the actual mass of that metal is going down. All right, and so that is then taking a neutral zinc and converting it to a zinc plus 2. Without the salt bridge, you're going to have a giant buildup of plus 2 zinc. You're going to have a huge plus 2 charge. And so in this, if you have KCl, the Cl minus is going to go into here and neutralize the zinc plus 2, so it doesn't have a buildup of charge. All right, so then on the cathode side, we have reduction. So what's happening here? Over here, we got the Cr plus 2, the nice blue solution, Cu plus 2, the nice blue solution, going to Cu solid. And so they're showing that picture here. Now your copper that's in solution is now going to end up on your copper electrode as solid copper. All right, so plus 2, when you make your copper plus 2, you could use it a bunch of different ways. Copper sulfate is very common. So CuSO4. All right, so in solution, it is copper plus 2, but you also have to have the counter ion. All right, and so over here, let's say we have copper plus 2, and then the counter ion is sulfate, SO4 minus 2. You could have picked copper chloride, you could have picked copper nitrate. There has to be some counter ion there that you dissolved that copper from. All right, and so when this plus 2 is now becoming copper 0, we have a buildup of the negative ion. So every time this happens, we have a minus 2 charge. It's minus 2 too much. It's minus 4. It's minus. It keeps going up and up and up. To neutralize this, the salt bridge, the K plus, is going to come in here to neutralize the sulfate as the copper deposits on the metal. And coming from copper plus 2 to copper, we have a K plus 2 that's going to come in and keep that charge neutralized, not building up a high charge on either side. That is the function of the salt bridge. In order for this reaction to go, we have to connect our 2 electrodes. Usually we do that with a voltmeter. Again, it could be a voltmeter. That's the usual case. So you can read what voltage is going across your cell. You can light up a light. You can, again, see what time it is on a digital clock. All right. So the salt bridge is a gel. All right. It's not a liquid. It would just fall through. It's a gel that doesn't let the 2 solutions mix, but it does let the ions flow. And so you can not get a buildup of plus or minus charge. All right, again, right, oxidation at the anode, red cat, reduction at the cathode. The ions that hang out at the anode are called anions. So ions at the anode are anions. All right, and so we know anions have a negative charge. Therefore, the anode has a positive charge. In order to attract these ions, the ions have to be negative. They're attracted to the positive. The ions that hang out at the anode are called anions. The ions that hang out at the cathode are called cations. All right, and so you have cations, and we know cations, they have a plus charge. So the cathode is negative, and that's why they are attracting the cations. All right, so the ions that go to the cathode are plus because they're attracted to that minus. They're called cations because they are the ions at the cathode. All right, the overall reaction is called a cell reaction. So when you add up your oxidation and reduction, that is in a voltaic, galvanic, or electrolytic cell, that is your cell reaction. And now we're going to finally show our electron flow. I drew it in on the last one. So the electron flow is through an external circuit, and electrons always flow from A to C, anode to cathode. All right, and so here we are showing the flow of electrons from our anode. Anode is always on the left. It's always the oxidation. The cathode is always on the right. It is always reduction. And so the electrons are flowing on the external circuit. So it is flowing from anode to cathode. And so that is your electron flow. And in this case, we've set up a light bulb, and it lights up your light bulb. And if you're doing the zinc copper, it gives out 1.10 volts. So again, your zinc, you can see it's decreasing in mass. You probably can't tell here. Your copper is depositing on here. You're getting an increase in mass of your copper. All right, and so this is building up a bunch of +2 charges. That requires your negative ion of your salt bridge to come down here, neutralize it. Your copper +2 is going to copper 0, so their sulfate or your nitrate, or your chlorine, whatever it is going to build up a bunch of negative charge as we make our +2 go to 0. So the cation of your salt will go in here to neutralize that charge. All right, so this is a typical, when I say draw, this is what I'm looking for you to draw. You draw a beaker, you have a solid metal electrode. You always have to have a solid metal electrode, something to connect to. All right, so both sides have to have a solid metal electrode to hook your alligator clip to. You have to have your salt bridge. And so again, on the left, it has to be the oxidation, the anode. The right has to be the reduction and the cathode. And so you will have to draw one of these cells. All right, here is the actual cell. If we do this in the lab, this is exactly what it looks like. We have our copper, that's a blue solution. We have our zinc, that is a colorless solution. We have our zinc metal that we clip our alligator clip to. We have our copper metal we clip our alligator clip to. We have a U-tube in the middle, and that is our gel with potassium nitrate is what I use. And then you then hook that to your voltmeter, and it will read 1.10 volts. If you have a 1 molar solution of zinc, a 1 molar solution of copper +2, you're doing your zinc copper electrode, it will read 1.10 volts. All right, so here's another voltaic cell. Voltaic cell means that it's spontaneous. All right, so we have a cadmium solid metal into a solution of cadmium nitrate. All nitrates are soluble. So we have a cadmium solid, and we have a cadmium +2. Another half cell, there's a silver rod, Ag+, or Ag solid, silver solid, dipped into a solution of silver nitrate. That all nitrates are soluble, and so we have Ag+. Of course, both of these are showing oxidation. They are not oxidation. One has to be oxidation, the other has to be reduction. One way we do it, it will be a voltaic cell. If we switch it and make the other one be the oxidation, switch the oxidation reduction, all right, then you would have an electrolytic cell. So if one has a negative delta G, you reverse it. The other one has a positive delta G. So in one direction, it's going to be spontaneous. The other direction, it will be non-spontaneous. All right, so here they're telling us the answer. They say that the silver ion is reduced during the operation of the voltaic cell. All right, so if you would have written it as the silver ion being oxidized or the silver metal being oxidized, that would not be a voltaic cell, that would be an electrolytic cell. So they're telling you the answer here. The answer is, if you want a voltaic cell in this case, the silver ion is reduced. All right, and so when we write it, it is the silver ion being reduced to the silver metal. All right, so the cadmium is being oxidized. This one's easy to balance because it simply add 2 electrons. There's no hydrogens, there's no oxygens. That's it. The silver half reaction, extremely simple to balance. We just need the 1 electron. So we plug in our plus 1 electron. And now before we would add them up, we would have to multiply the silver by 2 to get the overall reaction. We'd have to multiply it by 2 because your electrons gained have to equal the electrons lost. All right, so we can draw this cell. All right, so when we draw this cell, we knew that the cadmium was the oxidation because they told us that the silver was the reduction. And so we knew that it was going to be at the cathode. We knew it was going to be on the right because we were told that that was going to be the reduction. All right, and so the cadmium, if that's the reduction, the other one has to be oxidation. So at the anode, we have our cadmium doing oxidation. All right, so then you have your salt bridge. KCl is a good one to use for the salt. Remember that the Cl minus is going to go this way because this is taking the metal, solid cadmium, and putting the cadmium plus 2 in solution. You're building up a bunch of plus charge. You have to neutralize that by adding the negative ion of your salt. Here, your Ag plus is depositing, and they told us that this was silver nitrate. We'd be building up a high nitrate minus 1, minus 2. We'd have a high negative charge in there. And so to neutralize that, the K plus of our salt has to go in here to neutralize that charge. Of course, silver is not copper. All right, so they should have the cadmium is a silver color, and silver is also a silver color. It should not be a copper color. All right, your electron flow is always from anode to cathode. That is the way your electrons flow, and it's always on the external circuit. Again, you hook up a voltmeter, it reads whatever it reads here because this is not copper and zinc. If it's copper and zinc, it reads 1.10 volt. If it's cadmium and silver, we're going to get to that. We're going to look up our table and get what our voltmeter will read. All right, so you'll have to be able to draw a cell. You would sketch a cell, beakers, salt bridge, your anode, your cathode. They have to be metals. Let's see, is that coming up here? Oh, so we also have a shorthand. So when you have a cell notation, you're going to have your anode written first. Always on the left is your anode in your notation. Always on the left is the anode. And of course, the anode is your oxidation half reaction. Then you have this double line. I usually make mine slanted, but apparently it's supposed to be vertical. And when you have this indicates a salt bridge. So right here it tells you that that is a salt bridge. That separates your anode, oxidation half reaction, with your cathode. This is your reduction half reaction. Now, when you write your anode, you have to write it just as you did in your oxidation. Zinc neutral comes first, then zinc plus 2, just like you had your oxidation half reaction. But instead of an arrow, we're going to put a bar, but that bar does not mean an arrow. That bar simply means that you have a phase change. So a single line means a phase change. All right, so of course, zinc solid, that's a solid phase. Zinc plus 2, that's aqueous, that's a liquid phase. All right, and then over here you have your reduction where your copper plus 2 is going to copper plus 1. So you have to write it at that way. You have to write it as a reduction, a plus 2 to a 0. On the left side, you have to write it as an oxidation, the 0 first, the plus 2 second. All right, again, you have changed phases from the liquid aqueous phase of copper plus 2 to the solid copper electrode. So a single line means a phase change. The double line is your salt bridge, separating your anode from your cathode. If you do not have a metal for this half reaction, you have the reduction of H+. So 2H+ with 2 electrons goes to H2 gas. There's no metal here. There's nothing. You can't clip your clip to a gas. You can't clip it to a liquid. You have to clip it to a metal. When you do not have a metal in your half reaction, whether it's oxidation or reduction, you have to start with a solid. You have to end with a solid. If you don't have a solid to start with, you add platinum. If you don't have a solid to end with, you always add platinum. So platinum is the solid that you will always clip to, the metal that you will always clip to if your half reaction doesn't have a solid. All right, so it is inert. It is not going to change. It's not going to react with the cell. It is just going to be a point of connection. All right, and so it is not going to change the reaction. All right. All right, so here is your cell notations, and we can convert these to overall reactions. All right, and so here is our oxidation. We write it just as written. You have your TL solid going to TL plus, and of course, to balance that, we need 1 electron. All right, so that is your oxidation. The reduction half reaction is Sn plus 2 going to Sn solid. So you have your Sn plus 2 going to Sn solid. Here, we just need our 2 electrons. And that is your reduction half reaction. And then to get the overall cell reaction, you have to add them up. But anytime you add up an oxidation reduction half reactions, you must have the exact same number of electrons lost as gained. And so since we had 2 electrons gained, we had to multiply the first one by 2 to get the 2 electrons lost. And so the overall reaction, TL solid plus Sn plus 2 yields TL plus 2 TL solids, 2 TL plus Sn solid. All right, so you had to multiply through by 2, so you have a 2 here, you got a 2 here, you got a 2 here. The 2 electrons are gone. The electrons must cancel out before you add up your 2 half reactions. All right, and so that is your cell reaction. When you add up your oxidation and your reduction half reactions, you get your cell reaction. For the second one, you got zinc going to zinc plus 2. And to balance that, you need your 2 electrons. A very interesting one on the other side here. We got Fe plus 3 going to Fe plus 2. Note that this is not a different phase. It does not get the line, the bar. It is not a phase change. This is aqueous. This is aqueous. That's the same phase. If it's in the same phase, you use a comma. And so what we have is we have our Fe plus 3 going to Fe plus 2. And you see that requires 1 electron. All right, and so we see that the zinc, it gave off 2 electrons, but the Fe plus 3 to Fe plus 2 only required 1 electron. For electrons gained equal to electrons lost, we have to multiply this through by 2. And so now we have 2 electrons, 2 Fe plus 3s, 2 Fe plus 2s. And so when we add this up to get the overall reaction, we have our zinc plus 2 Fe plus 3s yields 2 Fe plus 2s and zinc plus 2. All right, and so you're going to have to be able to go from a cell reaction to a notation. Now note, in the reaction here, we have coefficients of 2 and 2. You don't see that. This is not a balanced reaction up here. You don't put the 2's for your coefficients. If you do, I'm probably not going to count it wrong. They should not be there. Same with your irons. It shouldn't be 2 Fe plus 3s and 2 Fe plus 2s. That's what we have in our cell reaction, but we're not. This is not a balanced reaction. These are just your ions that are there. All right. Whenever you have a aqueous, all aqueous is going to be in molarity. So we're always going to have a concentration. And so if no concentration is given, it is the standard state. All right, so the standard state is 1 molar concentration. If you are a gas, just like your KEQ, so gases will be in atmospheres. All right, if you are at standard conditions, you're at 1 atmosphere. If there is a different concentration given or a pressure given, you have to write what it is right after your ion. All right, so you're going to have your cell notations, but it's going to also have the molarities. All right, so here is an example of a cell notation that puts in molarities. All right, so if it is a standard cell, your concentrations for your ions are going to be 1 molar. So you can put 1 molar in for every single one of these that has a ion. Probably a good habit to get into, because if it's not 1 molar, it has to be there. If it's 1 molar, it doesn't have to be there. All right, same with your pressure. So your gas has to be in atmospheres. All right, again, if it's standard conditions, you don't have to put it. It's 1 atmosphere. If there is a pressure given, then you must put it in your cell notation. All right, and so for this cell notation, we have a zinc going to a zinc plus 2 and 2 electrons. All right, and so this one we have H plus going to H2. You have to know that you have to balance every reaction. All right, so the 2 is not put here, but it is required to have a 2 to balance the reaction. Again, the cell notation does not use the coefficients. If you would happen to put that there, I will not count off, but they should not be there. All right, and so that also required 2 electrons, 1 electron for each H. And so when we get the overall reaction, we have zinc reacting with 2H plus, yielding zinc plus 2 and H2 gas. All right, so that is your cell reaction. This is the cell notation. All right, so if you have a gas, the units are atmospheres. If you have aqueous, any ion in solution, your units are molarity. All right, and so right after the ion, in parentheses, you put the concentration. Right after the ion, in parentheses, you put the concentration. Right after a gas, in parentheses, you put the pressure in atmosphere. All cell notations must start with a solid that you can clip to. It must end with a solid you can clip to. Since hydrogen does not have a solid in this reduction half reaction, it is required to use a platinum solid. It is an inert solid that will not affect your reaction. All right. All right, so we are going to measure all of our different half reactions with a potential difference. All right, and the units for potential difference is a volt. All right, so we're going to have a chart. We're going to have a chart. It's going to have all these half reactions, and it's going to be giving you the voltage of these. And they are standard conditions, which means all concentrations 1 molar. all gases, 1 atmosphere, and 25 degrees Celsius. So your chart is going to have all of those numbers. All right, and when you have electrical work, that's your charge times your potential difference. Your SI unit for charge is the coulomb. The SI unit for potential difference is the volt. And the SI unit for work is joules. And so a joule is equal to a coulomb times a volt. So it is the charge times your potential difference. All right, and so this is the units. So this is simply a unit. A joule unit is equal to a coulomb times a volt. All right, we have a constant, and that is Faraday's constant. And that is the charge on 1 mole of electrons. That is a lot of sig figs. All right, 9.6485 times 10 to the 4th coulombs per mole of electron. That is the per 1 mole of electrons. That is the number of coulombs per mole of electrons. Not mole of anything else, moles of electrons. All right, so work is equal to negative your force times your potential difference. Your Faraday's times your potential difference. All right. So Faraday's is in coulombs, potential difference is in volts, but this is in coulombs per mole of electrons. So I don't know if I would use this equation exactly. You will have to get your coulombs from the number of moles of electrons times your potential difference. But this is the work per mole of electron. All right, so the potential difference across the voltaic cell is less than the maximum possible voltage of the cell. So we're going to calculate that you should get 1.10 volts. And then when you actually hook it up, you're going to get slightly less than that. All right, so it takes some energy, some work to drive the current through the cell, and that's going to reduce your voltage. So when you hook it up and you don't get 1.10 volts, that's not going to be a surprise. Okay. All right, so when we calculate our E cell, then that's what we're going to do. We're going to have our oxidation E value. We're going to have our reduction E value. We're going to add those E values up, and that's going to give us our E cell. This is the cell potential, or your electromotive force. So EMF, you'll see that a lot. That is just your electromotive force of the cell, which we will call the E cell. So EMF, E cell, that is the same thing. And this is the maximum potential difference between the cells. So we're calculating the maximum. So when we hook up our voltmeter and we don't get that maximum, it's a little less than that, we are expecting to get a little bit less than that. All right. So again, if you hook it up one way, you're going to get a positive voltage. You switch your 2 electrodes and you're going to get, so if it's 1.1 volts and then you switch it, it's negative 1.1 volts. All right, so going in the forward direction, if it's spontaneous, well, then going in the reverse direction is non-spontaneous. And that not only changes the sign of your E value, it also changes the sign of your delta H or your delta G value. Spontaneous delta G, negative. Non-spontaneous delta G is positive. All right, so when we're looking at the maximum amount of work, we know that work max, not only do we know this one now that it's written for us, negative NFE cell, from the last test, we knew that the work max was equal to delta G. So we know that delta G is equal to work max, and that is equal to negative NFE. Remember, F is Faraday's constant, 9.65. They used a bunch of different, whatever, 9.65 times 10 to the 4th, and this is in coulombs per mole of electrons. Units are extremely important. That will always be the case no matter what you're doing. Units are extremely important. So N is just not moles of anything. It is moles of electrons. So N here has to be in moles of electrons, not moles of the solid, not moles of the whatever. It has to be moles of electrons. And then you're going to have your E cell, your EMF, and that's going to be in volts. And so you're going to have moles of electrons, and this is negative, moles of electrons. That has to be a positive number. You can't have a negative moles. Faraday's constant, well, that's a constant, 9.65 times 10 to the fourth coulombs per mole of electrons, so that the moles of electrons, again, just putting mole there would not be good enough, moles of electrons. So that gives you a coulomb times a volt. And we saw that charge times your potential difference, that's your energy. A coulomb times a volt is a joule. And so if your E cell is positive, if that is a positive value that you get off of the table in this chapter, all right, then your moles is always positive. This is always positive. If this is positive, those three numbers multiplied together are positive, but there is a negative out in front. And so your delta G will be negative. All right. So if your E cell is positive, then your delta G is negative, and therefore the reaction is spontaneous. If the reaction is spontaneous and we're doing a cell, then we have a voltaic cell or galvanic cell. All right, so if it is spontaneous, then it would say it's a voltaic or galvanic cell. The delta G is negative. If your delta G is negative, your E cell is positive. And then, of course, if you reverse the polarities, you would get a E cell value that is negative. So if your E cell is negative, then, so that's a negative number. That's always positive. That's always positive. So you have a negative number times a negative number. That's going to give you a positive delta G. So then delta G is positive and it is non-spontaneous. And if you are non-spontaneous, then you have an electrolytic cell. So you need to know electrolytic cell is a non-spontaneous reaction. You have to give it current in order for, give it some voltage, give it some energy to make the reaction go. A spontaneous voltaic galvanic cell automatically gives off some voltage, and that's how a battery works. It's a galvanic cell. It is whatever, if you got a AA, AAA, it's going to give off the 1.5 volts. And then if you have a rechargeable one, you can then put it in a charger, and then that's going to do the add the energy to it to give it its voltage back, and it can charge and recharge over and over again. All right, so the way that we're going to do this problem is we're going to break it into two of our half reactions. So we see that we have Hg2 plus 2 going to 2Hg, liquid. All right, and so to balance this with electrons, we need 2 electrons. We also have H2 going to 2H plus. To balance that, we need 2 electrons. All right, and so we're going to look up our E values on table 19.1. All right, when you look up this one, your E naught for this one, you get 0 volts. This is called SHE. So your H2 going to your H2H plus 2 electrons. All right, so that is your standard hydrogen electrode. And your E value for that is 0. If you reverse it, the E value for that is 0. The standard hydrogen electrode, they set that one equal to 0. When you look up your Hg2 plus 2 going to 2Hg liquid, you get an E naught value of 0.650 volts. All right, and so that is your reduction potential. So this is your reduction half reaction. This is your oxidation half reaction. Now, when you're looking up the chart is only of your reduction potentials. It is a chart of reduction half reactions. If you want the oxidation half reaction, you've got to reverse it, and then you would change the sign of your voltage. All right, we did not have to change the sign of the voltage for this one because it was the reduction. We did have to change the sign, but it's zero. So zero, the opposite of zero, it's just zero. All right, so now when you add up your two reactions, here is your overall reaction. And to get the E cell, you simply add up your two E values. And so this is 0.650 volts. When you add your half reactions, you add the E naught values. Something very strange about this is if you multiply this, if it was 4 electrons and we had to multiply this through by 2. If you multiply any of your half reactions by any integer, so whatever you're multiplying it by, 2, 4, 3, 6, 1/2, whatever, never change your potential. So the amount is not going to change your potential. The voltage is the same. You multiply it by 2, voltage is the same. Multiply it by 5, voltage is the same. Never multiply your electrical potential when you are multiplying through your reaction. The voltage is the same as it was on the chart. That is never multiplied by any number. All right, so we want the maximum work. So that's delta G. That's equal to work max. And that's equal to negative NF E naught cell. All right, so you simply put in your 0.650. You put in your Faraday's constant, 9.65 times 10 to the fourth. Now you got to put in moles of electrons. So you have to write this reaction to see that you have 2 moles of electrons. All right, and so your N is equal to 2. When you have 2 electrons gained, 2 electrons lost, that is the 2 moles of electrons. And so that is your 2 moles of electrons. That's positive, that's positive, that's positive, times the negative. You're going to get a negative delta G because it says voltaic cell. Yeah, good, because voltaic cell means it's going to be spontaneous. All right, and so when you push the buttons, after you put all your numbers in, so you put in your 2 moles of electrons, your 9.65 times 10 to the fourth, and your 0.650 volts, you get volt times coulomb. You have to know that a coulomb volt is a joule. All you really need to know is this equation, and you also need to know that that's also equal to delta G. It is always going to be negative when you have a voltaic cell. All right, we will pick up here tomorrow.